Our channel has a huge problem. The internet does not think that we have the brain capacity to use stepper motors. And we actually have two huge problems because we have no idea how to use stepper motors. So we made this video to be a journey in understanding the physics of stepper motors, testing our intuition with a couple of science experiments, and then actually taking the steps to apply them to a project. Two, actually. This is every flavor of robot. Today's video has 4 sections, and we're going to be starting off with theory time. So let's get back into it, starting off with, what is a stepper motor? Big question. We're just going to be talking about NEMA 17 stepper motors today. Those are the ones that you find in every 3D printer. Those are the ones you see on every cheap CNC machine. If you go on Amazon and search stepper motor, you're probably going to see a bunch of NEMA 17 stepper motors. Now, if you're unfamiliar with that term, you're probably going, 17 who's it's? 17 NEMAs. It's named after the width of this square that someone decided is 1.7 inches, but that's not allowed, so we just keep it NEMA 17. When you take a look at these motors in the manufacturer's pages, they're going to tell you they have like 200 steps, they step at this angle, they're rated for some 24 volts or whatever. What we really want to know is, 1, what makes these motors tick? And 2, what can we assume about these motors? Because most of us have had that situation where we choose a motor and realize too late that it just can't work with the system we designed. Well, I have good news for you. All electric motors have the same few core principles. 2 physics principles and this 1 implementation detail are how they work. So our boy Lorentz, right? He came up with a way to describe the force on a wire in a magnetic field. And conveniently, a motor is actually just a bunch of wires in a magnetic field. But first, let's focus on just one wire for a second. His equation said, the force on a wire equals the current times the length of wire in the magnetic field times the strength of that magnetic field. Awesome. And to apply this to motors, we have to account for the fact that there can be any number of wires and that they're in a loop, so their length goes through the magnetic field twice. So all together now, we're ready to find the torque. We know that the torque is the sum of the forces times the effective radius. The radius is just diameter over 2, and so the torque is 2, to account for the double length in the loop, times the current times the length, times the magnetic field strength, all multiplied by diameter over 2. So now we can simplify this down to the coolest equation ever. The torque from a loop of wires is equal to the current times the length times the number of loops times the magnetic field times the diameter. Or as my grandma likes to say, torque equals current times all this stuff. We actually call this stuff KT, the torque constant, because you can't really affect it unless you're talking about buying or designing a different motor. But if I could wrap all of this into one sentence that I could sear into my own brain, it would be torque of a motor is proportional to current. Half the current, half the torque. So now, it's time to bring out another big word. Number 2, we got commutation. All right, commutation, I think, is an engineering topic that has way too big of a word for how complicated the topic actually is. Almost everyone understands this because you've seen a bicycle. The same way that a bicycle, whenever you press down on a pedal, eventually you reach the bottom of your pedal stroke and you need to switch legs. You need to change where you're applying your physical power. For an electric motor, you need to change where you're applying your electrical power so that it keeps being useful. Now in a DC motor, they use the spinning of the rotor to physically change the connections with brushes. And that way the current is always flowing in a direction that's perpendicular enough to the magnetic field that it generates a torque. There's lots of other ways to change the current, and especially now that we have easy access to tiny little computers and other electrical components, that's what brushless motors do. They switch the direction of the current in the motor. Just like a brushed motor, except with way less brushes, like 0 brushes. I can take this stepper motor off of this really stupid robot that was definitely not a hot dog robot. We can take it apart and count how many brushes are in here. And spoiler alert, it's 0. And it looks like it has 8 coils that are connected to 4 wires. Neat. My grip strength is not what it used to be. Oh. That is the inside of a stepper motor. The reason why I'm bringing this up is that the commutation is done electronically. We have these wires here, and we change the voltage on these wires with some circuit element in such a way that we can make this spin. But we're getting to why it's called a stepper motor. How many magnets, how strong the magnets are, the shape of the rotor, all of that determines how cleanly it's going to end up stepping or sticking to these detents. So great. What do we know about? Well, we know about Lorentz's equation, and we know about commutation. And now that means that it's time for, drum roll please, more theory. Come on, I said we're counting to 3. There's 3 core principles and we only did 2. It's like you're not even paying attention right now. The third principle is very related to the first one, and you've probably heard a thing or two named after Mr. Faraday, but here's another. There's a Faraday's law of electromagnetic induction that states, a changing magnetic field induces an electric current in a conductor. There are 2 really common examples of this. One of them is a generator, where we move a bunch of coils through a magnetic field, and due to Faraday's law, that power is stolen from the rotation and turned into a current. In a motor, we also rotate coils through a magnetic field, and due to Faraday's law, that power is stolen from the rotation and turned into a current. Isn't stealing rotation from the motor that we're trying to spin bad? Yeah, we call this the back EMF voltage. You can calculate just how bad as a function of the velocity times the length times the number of loops times the magnetic field times the diameter. Now here's a little trick they showed me in school. You can rearrange this. You can find that omega equals the voltage times 1 over the length times the number of loops times the magnetic field strength times the diameter. The cool kids called this little fraction the kV, or the speed constant of the motor. Are you having any deja vu yet? Wow, that's the coolest equation ever. Well, it turns out that's because they're very related. What blew my mind is that the SI units of kV and kT are actually the same. Usually we don't see them as in the same units, but deep down you can remember that if someone gives you one, you can calculate what the other should be. What's important is that we can now calculate the maximum speed for our motor, and all we need is the motor's kV rating and the voltage of our supply. Sweet. The other thing that this equation tells us is that the voltage generated against our power source is directly proportional to speed. So double the speed, double the voltage. Since voltage is what drives the current through our circuit, and we know that current through our circuit is what defines the torque, then we can say that as speed goes up, the torque we can apply goes down. So to recap before we move on, we started talking about NEMA 17 motors, but we actually just talked about motors in general. And the fundamental truths are that more current equals more torque, but only if properly applied via commutation, which is where we decide to apply electrical power. The third thing that we can be sure of for electric motors is that whenever they spin, they will act as an electric generator. And the voltage that they generate is called the back EMF. And the faster you go, the more back EMF you have to deal with. The bonus goodies that we got for doing this deep dive into the theory is the torque equation and the velocity equation. So, it's cool that we know about stepper science now, but I know what you're thinking. Yo, Alex, how do I actually get it to spin? Stepper motors are so easy to spin. All you need is your motor, some power, something that gives it instructions, and this little guy right here. We call this the motor driver. I built this breadboard in 10 minutes using this schematic, and after running 4 lines of Arduino code, the motor has both position and velocity control. Neat. Turns out all that theory stuff I was saying earlier is really easy to apply because a bunch of smart people have condensed it into this little chip interface. And the driver you see here is probably the most popular style of stepper driver that you're going to encounter. Because it's super cheap, it does all the math of the commutation, and you can power it with a super wide voltage supply. Plus, it only needs 2 signals for you to input, step and direction. So let's zoom in on this driver. If you've ever been in a mechatronics, robotics, or basic circuitry class, you've probably seen this diagram a whole lot. We call this the H-bridge circuit, and it's one of the most common circuits used in driving motors, pumps, or anything else where you want to drive current in one direction and then flip it to another direction. Your run-of-the-mill DC motor only needs 1 H-bridge, but stepper motors have 2 separate coils, or more than that, and need multiple H-bridges to fully control. But since we're here, let's zoom in even more. When you give the driver these 2 signals, it runs through this diagram to turn the motor. And we call this the commutation table. The order of it is very important because for a stepper motor to rotate clockwise, you need to step through it top to bottom. And counterclockwise, you actually have to step backwards through the table, bottom to top. Now this is a simple one that only has 4 rows, but you can commutate with more complicated tables. The chip can be configured to add half steps, quarter steps, all the way up to 16th or 256th steps in some drivers, and we call that process microstepping. Microstepping is basically what it sounds like, dividing each of your steps into tiny steps to increase the efficiency of your motor. We really recommend checking out these videos that we looked at if you want an even deeper explanation for microstepping and stepper motors in general. Man, aren't we glad that driver does all the thinking for us? But wait, there's more. People have also written code that's meant to work with these type of drivers, and it can do things like velocity, position, and acceleration control, somehow making it even simpler than it already was. Now that we have our stepper motor spinning and we got our basic code up and running, we can test our intuition with some science experiments. But before we get to that, I'd like to thank this video's sponsor, Onshape. I've been using Onshape for years now, started in college, and it's pretty much met all of my CAD needs. Whether you're doing professional CAD in a team or you're just getting started, it's very approachable and robust. Also, a huge shout out to our boy Tom over here, who has completely re-engineered the Etch-a-sketch to accept stepper motors, and we're gonna get back to his handiwork a little bit later. But back to the video. Instead of giving you the full report on like 1,000 little data points, especially since our test setup is kind of casual, what I can show you that you'll find useful is me walking through the questions that we were asking as we did these tests and what our thought process was whenever we saw the results. For example, the very first question that Swapnil and I sat around asking each other was, well, how fast can we drive a stepper motor? And we started out with this 12-volt test just because that's what the power supply was set at. Got the motor spinning. Best we could get was 330 RPM. Seemed a little bit low, but it had a lot of torque, and we were like, okay, well, what happens if we start adjusting the voltage? Let's bring it down to 7 volts. A lot of projects that we have run off of 7 volt or 7.5 volt power supplies. And strangely, the maximum velocity was the same, 330 RPM. It turns out our hypothesis was wrong. For some reason, the voltage is not defining the maximum speed. It didn't do what I expected. Let's just start testing some more stuff. So let's crank up the voltage. 20 volts, still 330 RPM. 28 volts, still 330 RPM. So that one was really strange. It came to mind that maybe it's kind of like a car. Whenever you slam on the gas and you start to lose traction, there's still power that the car can deliver. It's just not applying it in the right way to translate that into velocity. We also had a hint from our experience with printer slicers. In there's often a lot of parameter tuning around the acceleration of your stepper motors. So we kept the voltage at 12 volts and we adjusted the linear acceleration curve. When we did this, we found that when we brought it down to 100 steps per second squared, we had a lot higher RPM, and then we saw it keep going up. And at our top voltage of 28.8 volts, because that's where the power supply starts to stop, we got 2,700 RPM, and that is a lot better than 330 RPM. That's a lot faster than I ever thought I would see a stepper motor spin. And now finally, voltage is the defining factor of velocity, just like we would expect from our characteristic motor equations. To me and Swapnil, this was kind of like a nice moment. We're like, okay, stepper motors aren't black magic. They follow the basic principles of physics. So now we're thinking, if software acceleration has such an effect, does reducing the microsteps have that big of a difference? Should I really look for chips that always have microstepping? And so we disabled it from 16 to 1. We kept it at 100 steps per second squared, and we started increasing the speed. Yeah, it was only about 100 RPM slower. I mean, that's not very much at all. So yeah, it in fact was slower, but just not by much. Okay, we're just gonna put a pin in that for now because there's this other thing that we need to test. None of the robots that we're trying to make with stepper motors are going to just be a gear spinning around in free air. We're almost always going to have a load on them. We need to make sure that we still have torque at a reasonable speed. So we built something here to accurately and precisely test the torque of these stepper motors. Introducing the totally professional torque tester. We're just gonna hold this string as the stepper motor turns, and the string adds, it's so like there's like friction on the, because the string is like wrapped around. So what did we learn from doing this 25 times? We did 12 volts, 16 microsteps, and boom. The average probably somewhere around 500 RPM. This is the average velocity that we got at what we deem a useful torque. And by useful torque, we mean whenever we returned it, we're like, oh, I could use that in a robot. Like I said, this is a qualitative test. So we're doing the best we got. So then we lowered it down to 7 volts. We did the same test. Honestly, I was expecting that 7 volts should be enough to hit the current limit of the stepper driver, which is 2 amps. So I didn't expect the useful torque range to go down, but it was definitely lower, about 300 RPM. So then we're like, okay, let's jump it up. Let's go ahead and finish the test. We hit 20, put us back in the 500 range. So that was basically conclusive enough for us. We're like, okay, 7 volts, obviously not enough for this system, but 12 volts or higher is good enough to hit the current limits, and that's where we're actually being limited by the windings of the motor themselves. And that's what we wanted to know. What is the limit of the motor? Now, there was one more loose end that we wanted to figure out. We saw that changing from microsteps to full steps didn't really affect our maximum speed, but we were curious if it affected the torque. And it turned out under load, we had nearly half the useful range. Again, this isn't super rigorous, but we did notice that there was just a substantially lower torque that you could apply on this system before it would start to get out of sync with the driver. And that was really surprising to me. Microstepping makes a huge difference in the quality of your motor controls for stepper motors. For me, I think I'm going to be sticking to the rule of thumb that underneath 1000 RPM is pretty achievable with stepper motors, but closer to the 500 and below RPM range is going to be when I will, from now on, immediately go to stepper motors. Okay, we're finally to the fun part of the video, because what's the point of building all this intuition and doing all these math problems if we're not going to actually use them to build some robots, right? This is supposed to be every flavor of robot. We're supposed to build some robots. Man, I'm really debating if I want to tie our brand that heavily to hot dogs, but here we are. I think this is where stepper motors just absolutely shine. They are really fast for prototyping. Next robot. This whole video started because someone pointed out that I don't know how stepper motors work. Well, now they can't say that anymore. I feel like I know how these things work. We tossed some stepper motors on the Etch-a-sketch and ran some tests.
Alright, so I've tuned it up as fast as I was able to get it to go stable.
Okay.
Let's get this camera out of the way. We don't need that. I don't know what it's going to draw. It's going to draw whatever you sent me, dude.
Oh, really?
It's called hotdogrobot.svg.
Yeah. Okay. This is real speed. It's just not real speedy. I don't know how much of this I should cut out for you, but this is taking a long time. Right. You won't. Trust the process.
It's a robot dog.
Well, yeah, actually, it totally is. It is a robot dog. R.
I like that it makes the, like...
Here's the R.
No, they turned out. I can see them. I can distinguish them.
Only because I told you, though.
Yeah, if you didn't tell me they were letters, I wouldn't have known. but I could totally, as soon as you said they were letters, I knew what it was. You know?
Okay, this is pretty much the end of the test. The motor driver is actually seized up here, and we don't exactly know why, but this is what we were trying to draw. And the stepper motors did a really good job, especially considering they had no sensors or anything like that. It was just raw stepper motors on an Etch-a-sketch. But just to compare them, because we can, we have the original Etch-a-sketch from our last video running with full closed loop control and motors that are tuned for this system.
So fast.
I think the biggest advantage from going to a brushless servo system is going to be the top speed, and we really see that on the big motions, this Etch-a-sketch just flies through the motion. While this is drawing, we'll also bring up what the stepper motors look like side by side for a second here. So it's pretty clear that the brushless motor controlled Etch-a-sketch is moving a lot faster, but it does look like the stepper motor Etch-a-sketch has a little bit cleaner lines. We do think we know how to fix this, however, and you should stay tuned for the upcoming video where we're going to revamp the Etch-a-sketch robot.
This is disgusting sounding. I just lost the cursor.
You gotta admit, it's a pretty sick demo, right?
Yeah. Pull down the cursor actually and it disappears.
I'm pretty impressed with our servo system here, but honestly I'm also very impressed with how close the performance of the stepper motor system was, considering that it took substantially less time. I hope you found these tests as insightful as I have. This video was just like one small little blip on the map of robotics that we are working on. And if you want to help us make more of these videos that explain deep dives into topics, consider joining our Patreon like these amazing people right here. And that's all for now. I'll see you all next Wednesday.